Aloha and welcome to our video on waves and tides. In this video, we'll describe how ocean waves get their energy. We'll state the three factors that determine the characteristics of a wave. We'll describe how energy moves through a wave, and then finally we'll explain forces that produce tides. Most waves are going to be caused by winds. So what you're going to have is this wind blowing across the surface in this direction, and that's going to generate these waves, and that's where we see the direction of wave movement. So even though if we have a lot of wind like a storm here, it's going to start the wave moving, and that wave's going to continue in this direction. And you can try this at home. Just take a bowl of water and a straw and just blow on the surface of the water on one side of the bowl. You'll create waves that'll travel to the other side of the bowl, and that's kind of what we're talking about here. Now, when we're talking about waves, there's a couple different pieces and parts I want you to know. We have a wavelength, and the wavelength is going to be the measurement from a point on a wave to the same point on the adjacent wave. So here we're measuring from the top of the wave, which is what we call the crest. And if we go from the crest of one wave to the crest of another wave, that's going to give us our wavelength. Now, the crest is the high point, the trough is going to be our low point, and the difference between the crest and the trough is what we call our wave height. Okay, so that's what we're looking at for properties. You kind of want to know the wavelength, the crest, the trough, or the wave height. If we notice on the surface, because we're moving these particles, notice we have these circular orbital motions. We're seeing this water particle is going to travel in these circular paths. Notice the water doesn't move. What we're seeing is the water moving in an up and down manner rather than continuously moving in one direction. And I know that's contrary to what we said a little bit earlier in things like upwelling, where we're moving the entire water. But here we're just talking about how that wave can be propagated and how it continues and travels across the ocean. Okay, so let's see what happens with a wave when it transfers from deep water to the shore. And deep water, notice that the range of depth that the wave can actually impact the particles is constant. It's not hitting anything, it's out in the ocean. Notice all the waves are kind of uniform in wavelength and wave height. It kind of works that way. As they get close to shore, this circular here, these circular motions, this depth that the wave can travel through, this energy disturbance starts hitting the bottom. And as it hits the bottom, it drags across the bottom and it causes the bottom part of the wave to slow down. And we can see here we have a nice uniform wave, but as we're starting to drag, you start seeing how the top of the wave is able to move faster than the bottom of the wave. And ultimately, that's what causes it to break on the shore, which is what we see. So that's pretty much waves. Most waves, like we said, are going to be caused by winds that are blowing across, and they'll cause these disturbances. And as these disturbances get close to shore, the bottom of them starts dragging on the shore, and we see these waves breaking. Okay, let's move on to tides. Now, the biggest force that causes tides is going to be our friend the moon out here. And the moon has gravity, the earth has gravity, and if the earth's gravity is pulling the moon's gravity is also pulling the earth. As it does so, it's able to pull the water, and we're going to cut the earth in half. Okay, we're going to cut the earth in half this way. And it's going to pull the water on this side of the earth here to form this little tidal bulge here. We'll notice that bulge there. Okay, so this is where we're going to have high tide because there's that bulge there. And then where there's no water is where we would have a low tide. Now on the opposite side, we also notice there's this bulge. And the reason we have a bulge on this side is because the earth itself has been pulled and left some water behind. So we have the tidal bulge on the side of the moon from where the water's being attracted, and then this tidal bulge on the opposite side of the earth where the earth is being attracted and left the water behind. So that's why when we look at our picture, we have our earth here. We're going to have a tidal bulge on the side of the moon, and we'll have a tidal bulge on the opposite side. And then these are our areas of high tide. Okay, so this is where we have a high tide here, and where we don't have the water is where we're going to have our low tide. Okay, so we can kind of see it that way. Now remember, the earth rotates, so as the earth is rotating, it's rotating through these tidal bulges, and that's how we have a high tide and a low tide going on throughout the day. Now you'll often hear when we're talking about tides, and in the lessons, you'll hear of what we call a spring tide and a neap tide. Okay, a spring tide is where we have a pronounced tide. So notice here, we're going to look at our picture. We have the sun here and we have the moon here. Now remember, the moon causes the lunar tide. Lunar is going to refer to the moon, and that's where we have the biggest bulge of water. But we also have a solar tide, which is caused by the sun. So even though the sun is so far away, remember it's so massive, it has such a force of gravity that it's going to create a little bit of a solar tide as well. In a spring tide scenario, when we have a new moon or a full moon, notice how the moon is lined up with the sun and the earth. So we form this solid line that goes through all three objects. In this case, that means that the lunar tide is being added to the solar tide, so we have a pronounced, a larger tide, and that's what these spring tides are going to be. Okay, so that means that if we look at the Earth here, we're going to have the solar tide, which is going to be a smaller bump here, but added to that the larger bump of the lunar tide. So because both of them are together, it's going to be a greater tide, and that's what we call our spring tides. Now, we notice here we also have a neap tide. In a neap tide, we have our line from the Earth to the Sun, but our line to the Moon is going to be perpendicular to it. So now we have the pulling of the lunar tide here and the pulling of the solar tide here, so we have less going on. If we were to draw this, we have our Earth here. We're going to have our solar tide bumps here, and then we'll put in our lunar tides here, and notice that it's not as pronounced as it was in the spring, so we have less tide, and that's going to be our neap tides. So spring is when everything lines up. Neap tides are when we have this perpendicularity going on right there. Now we can define the tidal pattern by how often we have a high and a low tide in a 24-hour period. So notice here we have the diurnal tide pattern. And the diurnal tide pattern means that in a period of 24 hours, we have exactly one high tide and one low tide. Okay, we also can have a semi-diurnal tide pattern, and this one in the same 24 hours, notice that here we're going to have two high tides and two low tides. Okay, so it happens in a semi or a part of a day. So this is a full day tidal pattern, this is a part day tidal pattern. And then we end up with also a mixed tidal pattern. And in a mixed tidal pattern, notice that we are going to have our two high tides and our two low tides, but notice how we have a significant low, we have a low, we have a high, and then we have our significant high. So it's going to be kind of mixed in the highs and the lows, but it's going to run on the semi-diurnal pattern. Okay, that's it for our video. As always, you'll get more information in the lessons. Good luck on your quiz, and we will see you in the next video.